Okay, so we took a look at the electron acting as a particle in the Bohr model. The quantum mechanical model of the atom thinks about electrons as waves. So if we're thinking about a string and we wave it up and down, eventually you can get something that's known as a standing wave, where basically you have the string waving up and down, but the 2 points at the end don't change. Let's pretend that has a wavelength of lambda. Now we can also do the same thing with the string, but this time if we wave the string faster, what we get is we have a standing wave with half of the wavelength and 3 points that don't move. Again, we can do it even faster and we can get 4 points that don't move and a wavelength that's a third the original wavelength. Now, if we think of that in terms of 3D atoms, we can actually form our models of electrons based on these patterns. So a 3D model would look like a sphere, a little dumbbell shape, and then the third one gets a little bit funky looking. Some sort of look like that. And then others sort of look like flowers. Now this is actually what electrons are theorized to look like in the quantum mechanical model. So each one of these shapes is known as an orbital. It can hold 2 electrons, and based on the different shapes, we give them different names. So the s orbital is the sphere orbital, and there's only one type. The dumbbell orbital that looks sort of like a helicopter blade is known as the p orbital, and there's actually 3 different flavors of p orbital. One along the x-axis, one along the y-axis, and one along the z-axis. And then lastly, the d orbital, those weird flowery looking orbitals, have 5 different possible shapes that they can be in. Oriented along various axes. And these shapes are actually the probability of finding an electron with 95% certainty. Now, in chemistry, instead of having to draw all of these shapes each time you want to represent an electron, what we do is we change these shapes into squares just so that it's an easier way to visualize. So this square in chemistry represents an orbital. It holds 2 electrons at the most. And what we can do is we can represent these electrons using these one-headed arrows. So this one-headed arrow represents an electron. And electrons have a property that you need to know about called spin. And basically, electrons can either have their spin up or have their spin down. And we represent their spin up as shown there and spin down also shown. So for example, what we can say is an electron can be found in the s orbital in the first main energy level. And we write that as 1s. So again, within each of my main energy levels, I have a bunch of orbitals of different shapes. These shapes are named different letters, and they're also known as subshells. The number at the beginning tells me the size, and the subshell tells me the shape. Let's just take a very quick look now at how we can draw orbitals properly. So again, usually we draw one electron with the arrowhead pointing to the left. It's okay if you draw them pointing the other way around, but please don't draw double arrowheads and please don't draw single arrowheads horizontally. Those are both wrong. In organic chemistry, we're going to see exactly why we use single arrowheads. Now again, if we want to represent 2 electrons in an orbital, the green is what you should do, and the red is what you shouldn't do. So you should never have 2 electrons that have the same spin in the same orbital. Okay, now to build orbital diagrams, the next step that you need to do is build the frame. So we can label our energy levels from lowest to highest, 1, 2, 3, and 4. And within each of these energy levels, we have different sublevels based on the shape. On the first one, we only have S, the second one SP, the third one SPD, and the fourth one SPDF. After that, we add in the different orbitals, remembering that S only has one flavor, one type. P can have 3 different orientations, so we show 3 different boxes for each of those orbitals. P, X, P, Y, and PZ. The third energy level has S, P, and D. So let's draw that. So we have our 3s, 3p, and then this is an exception. Our 4s is actually lower than our 3d sublevel. So this is a little bit tricky. You have to remember that 4s comes before 3d in your orbital diagrams. Okay? The last step that we do is we separate these orbitals based on their sublevels. So we're going to put our S all the way to the left, our P in the middle, and our D all the way to the right. So our 1s is going to be in that space, our 2s is going to be above that, then our 2p, our 3s, our 3p, and don't forget the exception, our 4s comes next, and then our 3d. Okay? So that's how you build the frame of an orbital diagram. Make sure you can do this quite quickly. And now we're going to take a look at how we fill electrons within this frame. So there's basically 3 principles and 2 exceptions that you need to know. When we're filling in our orbitals, the Aufbau principle says that if boxes of different energy are available, the electron goes in the lower energy orbital. So that's the one closer to the bottom of your page. So for example, if we had these 2 orbitals, you would not put your electron in the higher energy level. Hund's rule says that if we have boxes of the same energy, so let's pretend we're talking about Py, Px, and Pz, those guys are all the same energy. Hund's rule says that if we have an electron and we want to add another electron to the same energy level, we want to make sure that it goes in an empty box first before they start pairing up. This is because electrons are negative and they don't like being around each other unless they have to. The last idea is Pauli exclusion's principle. So this is the idea that both electrons can't have the same spin. So we need to make sure that in the same orbital, my electrons have an opposite spin. Okay, so let's talk about the exceptions that you need to know. Let's specifically look at copper, and then we'll take a look at chromium. So copper has an electron configuration of 4s3d9. Okay, now it turns out that the 3D sublevel is a lot more stable when it's either full or half full. So what happens is one of the electrons from the 4s is promoted to that last 3D orbital, and this overall configuration of 4s1 3d10 is actually a lot more stable. In terms of chromium, what happens is we have an almost half full. So we have an almost half full, and one of the electrons from the 4s goes up, and so it becomes 3d5.